This is Module 12, Lesson 6. What we're going to look at today is two additional gas laws. We're going to look at the ideal gas law and Dalton's law of partial pressures, or you can just call it Dalton's law. So, first of all, let's start with the ideal gas law. The ideal gas law is based on the principles that we learned about gases back in Module 12, Lesson 1, where we talked about the properties of gases, that they're made up of solid spherical particles, that they move rapidly and randomly, their collisions are elastic. All of those are ideal conditions, which means it's not realistic. It's a perfect world. This ideal gas law is based off of everything working perfectly just like we assume that gases do. Now, you should already be familiar with three of these pieces, the P, the V, and the T. We used those in the previous lesson where we had the combined gas law. That was P1V1 over T1 equals P2V2 over T2. So P still stands for pressure. Capital V still stands for volume. And T still stands for temperature. The new things to this equation are the N and the R. N stands for the number of moles of gas that you have, and R is called the ideal gas constant. So we need to talk about units before we move on and learn how to use this, because the units are what are going to allow us to pick this formula out of our reference table list of formulas to know what we need to solve a problem. The pressure for these particular problems can still be in kilopascals, millimeters of mercury, or atmospheres. Any of those is acceptable. Like, you can use any of those three. Volume this time has to be in liters. In our previous equation, we could use milliliters as long as we use the same thing on both sides of the equation. But this one only has one volume. We absolutely have to have liters. Now, the number of moles, that's pretty easy. The unit will be mole, of course. And temperature still has to be Kelvin, just like it did in our previous equation. All right, so what about this ideal gas constant thing? Well, on your reference table, you have the gas constants. This is the very first page of your reference table that you get with every test and with the NC final exam. The gas constants are listed here. Now, there are three different versions of the gas constant, and I know, like, the numbers are very different. If you take a moment to look here, you will see that the only difference between these is the unit of pressure that's in there. You have atmospheres, millimeters of mercury, and kilopascals. Every single other thing about this is exactly the same. So if I change my highlighter color here, look, they all have liters and moles Kelvin, and I've made my little window pop up. We've got liters, moles Kelvin. We've got liters, moles Kelvin. Like, they all are common with the liters and the moles Kelvin. What's different about them is their unit of pressure. So, how do we decide which of these things that we are going to use? We're going to base it on the unit of pressure. If the unit of pressure in our problem that we're given is atmospheres, then we'll pick this first one. If our unit of pressure is kilopascals, we'll pick the second one. So here's an example of how this would work. It says, what is the volume of 42 moles? So 42 moles is a number that we have. We've got moles right here, so that's going to be our N. And it started out with this question, what is the volume? So we're hunting V. Of oxygen gas at this many atmospheres. Well, atmospheres measures pressure, so that's a P. And this many degrees Celsius, that's going to be a T for temperature, because temperature is measured in Celsius. So if you are doing this on a test, and all these formulas are going to be mixed up together, what you're going to have to decide is which formula to use. Am I using this formula from the previous lesson, or, oops, that's a one, or am I using this formula from today? If you stop and look at it, I don't have two pressures, I don't have two volumes, I don't have two temperatures, like, I don't have two of everything. Plus, I've also got this mole thing in here, and moles has nothing to do with this one. So this is out, this is in. So what we're going to do is we're just going to plug into this. For the P, we'll have 0.490 atmospheres. V is, let's see, right here, that's what we're finding. N is 42.0 moles. Now, what do we do with this R? If we go back a slide, well, let's go back to this one. Our pressure here is in atmospheres. So this one right here is in atmospheres. We're going to use this one. So I'm going to copy down everything it says, 0.0821, and then it has liters, atmospheres over mole, Kelvin. Now for this first one, I'm going to include all the units. I mean, you don't have to, but they certainly help you figure out what you've got. Okay, so after this, that's our R. We now need temperature. Now, don't forget, like, we cannot use degrees Celsius, and one of the reasons that we can't use degrees Celsius is because this is in Kelvin down here. I need my units to cancel out. So it has to be in Kelvin. So we add 273 to it, and we get 351 Kelvin. Now, to do a little bit more additional work than I normally would, because not everybody has the same math skills, don't forget that you could see this whole thing as a fraction. It's this over moles Kelvin. I can also imagine that this is over 1 and this is over 1, because we can put any number over 1. If I do that, these two moles, they'll cancel because this is in the numerator and this is in the denominator. Kelvin will do the same thing. Kelvin in the denominator, Kelvin in the numerator. They cancel each other out. If I wanted to rewrite this for just a second, we could write it this way, 0.490 atmospheres times V. I'm going to put all of my numbers together. 42 times 0.0821 times 351. And then if you pretend like this is algebra class and these units are your variables, liters, atmospheres, that's what's left over. So what's next? You could do math, of course, but I'm going to go ahead and get the V by itself. In order to get V by itself, I need to divide what it's being multiplied by. You do the opposite. If you're multiplying by 0.490, then you divide by 0.490. And what you do to one side, you have to do to both. So if we divide both sides by 0.490 atmospheres, this cancels on this side, and over here, the atmospheres cancels. Well, what does that do? That leaves me with just liters. And that makes sense because we're finding volume. Volume is measured in liters. If you would end up with like volume in atmospheres, you've done something wrong. So if you go to the trouble of doing all of this math, and of course putting it into your calculator correctly is going to be half the battle sometimes so that you get the right answer, you will get that this is equal to, I don't have it in front of me, so I'm punching numbers, I get 2470.03 and a bunch of other stuff. So, can we leave it this way? No, we've got to have sig figs. So, if we look back to our original stuff, this has 3 sig figs, this has 3 sig figs. This would technically have 4, because once you add it, if you do this and add it to 273 Kelvin, like 273 Kelvin is an exact thing, like it would have 4 sig figs. So 3 is less, so we can keep the 2, the 4, and the 7. So that's going to change it to 2,470, and then the unit we're left over with is liters right here. So 2,470 liters. That's our answer. And oops, I skipped on ahead. So hopefully everybody's good with that. If you have questions about the algebra or the sig figs, please ask. Now this next one, I'm not going to do all the units in it. Like, you don't absolutely have to. But here's another example of this. How many moles? Right, here's our question. So how many moles is going to be in? We're finding in. As soon as it says this, I'm thinking like it's either a mole problem or it could be this ideal gas law thing. Would have a volume of this many liters. So that's V at 460 millimeters of mercury. That should be a capital H. That's pressure. And this many degrees Celsius, which is temperature. So when I see N, V, P, and T, I know that once again I am plugging it into this particular equation. PV is equal to nRT. Our pressure this time is 460. Our volume is 3.8. Our number of moles we are finding. Now it's time for R. how do I pick it? I use the unit of pressure that's in my problem. This is millimeters of mercury. So if we go back 2 screens, this time we are using this one right here, second one. We're using the 62.4 because it's in millimeters of mercury. So coming back over here, we've got 62.4, and then this time will be 350 Kelvin, because 273 plus 77 is 350. Now, it looks a lot less scary, and I don't know why I put the Kelvin on there at the end. It looks a lot less scary, in my opinion, without all of those units in there. It looks a whole lot easier. You don't have to put the units, but what I do have to do when I get to the end is know what unit I'm going to have. So on this particular one, keep in mind that to get N by itself, you will have to divide both sides, in this case, by 62.4 times 350. That cancels them out on the right-hand side and gives us our math problem on the left-hand side. Don't forget that if you're going to do the 62.4 and the 350 at the same time, to put them in parentheses so that you don't mess up your order of operations. Good idea to put the top in parentheses as well. If you do it properly, you'll get 0.08003 and more digits. If we go back to sig figs, this has 2 and this has 2. This has 3 and it would have more when you convert. So 2 is less than this could ever be. So remember that with numbers that are smaller than 1, you start from the first non-zero and count to the right. That means I can keep the 8 and the 0. So our final answer will be 0.080. Now, I don't have any letters up here this time, so I just have to know that N is moles, and my unit would be in mole. So this would be my answer for this problem. So now, on your paper, you have some practice problems dealing with PV is equal to nRT. You have answers on the page so that you can check your work as you go. And then you're going to come to another section called Dalton's Law of Partial Pressure. You can either keep watching and do both of these at the exact same time, or you can pause the video, do the ideal gas law problems, and then come back to watch the rest of it and do the Dalton's Law problems. That's up to you. So Dalton's Law of Partial Pressure is actually really simple. It's also on your reference table. Some people just refer to it as Dalton's Law. The whole idea behind it is that a total pressure will equal to smaller pressures that make it up. This ... means you could have 3 pressures, 4, 5. It might just be 2. You might cut it off at P1 plus P2. So these problems could be as simple as telling you that you have, 3 gases mixed together. They each have a pressure of 2 atmospheres. What's the total pressure? So if that's the case, if you have 3 of them, each with 2 atmospheres, you would just add up, 2 plus 2 plus 2, then the total would be 6 atmospheres. Voila, like that's Dalton's Law. Occasionally, though, the problems can look more complicated. So sometimes your problems are going to tell you that gas was collected over water. And I want you to understand exactly what that means. So if you see a problem that's phrased like this, you'll go, oh, I know exactly what they mean. Okay, the problem with collecting something that's a gas is if we just had a beaker sitting out here on the counter with the bottom of it down here, like here's our, our countertop, and we try to run a tube down into this beaker like this with bubbles coming out of it, is that the beaker or the cup is already full of air. You have a mixture inside of this empty container of mostly nitrogen, some oxygen, some water vapor, some carbon dioxide. Like, it's not just the gas that's coming into this tube that's going in the container. So how we fix this is we fill a container with water, like this one right here, like this container right here that's upside down in this like a, some sort of a dish of water. And what they've done is filled it all the way to the top. And they have a gas bubbling through this tube right here. It's traveling all the way down and bubbling up right here. And what happens as it bubbles through the water is it fills up the top of the container and it pushes the water level down. And the more gas bubbles that go in, the further the water level goes down until you get over here. And if you continue to bubble it and let the bubbles come all the way up, the water level will go all the way out the bottom of it. And when it does that, you'll have a container of just the gas that you wanted to collect. The problem is that inside this container, you have the gas plus you have some water vapor. And because the gas gets wet, as it bubbles through the water, it attaches little water particles to it. So it's not dry gas, it's considered to be wet gas. So what you'll see is problems that say this. They'll give you some information like a 250 milliliter sample of oxygen is collected over water. Here's that phrase. At 25 degrees Celsius and 760 millimeters mercury of pressure. What's the pressure of the dry gas alone? So the two things that I have circled and underlined help me to know that this is one of those Dalton's Law problems where we've bubbled gas through water and the gas is now wet. And so the bottom line idea is that the total pressure is equal to the pressure of the water vapor plus the pressure of the dry gas. So the total pressure right here is the 760 millimeters of mercury. Okay, it tells me the partial pressure. A partial pressure is just one of the pressures that makes up the total. The partial pressure of water vapor is 23.8 millimeters of mercury. Now this is specific to 25 degrees Celsius. If you change the temperature, you'll change the pressure of the water at those temperatures. So if it asks us to find the pressure of the dry gas, all I have to do is subtract. I mean, it's that simple. The hardest part of it is figuring out which of these numbers I want to use. So our pressure that we're looking for is 736.2 millimeters of mercury. Now, a quick sig fig lesson here. Remember that when you subtract and add, it's about the number of decimal spaces. So this is what my calculator says. And remember when we did this, we talked about the idea that if I had 1 decimal space on this one and 1 decimal space on this one, then I could have 1 decimal space in my answer. Do not cut this down further because our addition and subtraction rules say I can keep everything up to that 1 decimal space. So this would be my final answer. Now, another word about this. What's usually confusing for students is what I'm getting ready to highlight. What's confusing is, well, I don't want it in red. What's confusing is this part right here. Let's put it in like yellow, it'll be easier to see. Is this. You have this milliliter, you have this temperature, and so students want to start turning this into something like PV is equal to nRT. So for just a second, let's consider this. I'm still on the highlighter. What if we tried to put this into PV equals nRT? Part of it is I have two pressures. I have a pressure here and I have a pressure here. And you can only have one pressure for this particular formula. It also never mentions moles. And that's, I mean, all of those things are telling me it's not this one. If I wanted to put it into PV over T equals PV over T, hopefully this isn't too hard to see. If I tried to put it in this one, the problem with that is I need at least two things. I do have two pressures, but I don't have two temperatures. I don't have two volumes. So unless I come up with like two different things, like this isn't going to work, this isn't going to work, it's going to have to be this. The other thing that tells me that is the over water and the pressure, the dry gas alone. Excuse me. So you have some problems with these as well. So it is now time for you to practice those, or all of them if you've waited until this point. You have the answers on your paper. I'm also going to post for you a review sheet that has these mixed up and has them with no answers in case you would like to try your hand at making sure that you know which formula to use, and you know that I'm available during office hours if you need me to work these with you.